Hello learners, I hope the geography at school is going well and the studies are going well, and we're going to definitely get those grade 11 marks up so that we score a huge distinction in grade 12. Today what I'm going to look at is the topographic map interpretation. Obviously it's going to involve a lot of calculation and identification of features, etc. I find this a common problem. And sometimes before learners write exams, I try to hide myself away because what do they ask me? Sir, do you have a protractor? Please to lend me. And I've lost thousands of protractors over the years. Sir, do you have a calculator to lend me? Do you have a ruler to lend me? Do you have a pencil to lend me? Do you have a piece of string to lend me? And they forget a piece of paper. And of course, I always like this, if you can, if you got good eyesight, is fine. But as I say, if you like me with bad eyesight, you definitely need to carry this so you can look at the map. So in other words, what I'm saying, learners, is make sure you have all the necessary equipment with you before you write your exams. Anyway, let's not waste a lot of time now. Let's go on. Okay? And topographic map. In the session of the past, we spoke about topographic maps and in relation to aerial photographs. Now we're going to look more specifically at the topographic map. Okay, some key concepts that we will be focusing on. Of course, we'll be locating the, let me get my pen on, we'll be locating the exact position in degrees, minutes, and seconds. We'll also look at relative position in terms of direction and magnetic bearing. I do know that lots of these concepts are not unfamiliar to you. Okay. We also will be looking at scale and the types of scale. We'll also be looking at distance, measuring of straight line distance. Okay. I think that's some good news for you. It gets rid of the paper method and a little piece of string, but it's nice to practice in class. Calculating of area, using of map index, locating places on different parts of the map, using degrees and minutes. Remember, there's two methods, degrees, minutes, and seconds, and degrees and minutes, and we will combine them. I'm just following this system here because that's how it is in your curriculum. Comparing information from different maps. Of course, we'll have to relate our map to the orthophoto map. Contours and landforms, which I'm going to bring towards the end of my presentation. Okay. Cross sections. This section here, I know, makes you very cross. I think that is why we call it cross sections. But we'll do some simple stuff. In order, we'll attempt rather to try and get a better understanding of cross sections. Vertical exaggeration, intervisibility, gradient. Okay, learners, let's go through it. Some important points, and I know I may have repeated myself. I'm repeating myself, and I've said it before. Okay. We do not look at the map in isolation. We use the topographic map with the photograph. Okay, this section involves calculations and drawing of cross sections. Make sure you have all the necessary equipment. Okay, let's start off with the first little section, coordinates. Some of you know it as grid reference, and the future curriculum talks about grid referencing. Do you understand? A very common question. Lots of times it comes out in the multiple choice, sometimes in the calculations. All right. And I know it gives learners a little of a problem. So what I'm going to do is I've got a little explanation here for you, step by step. And if you just follow it, it's actually not a very difficult concept or calculation. All right. First of all, when we look at it, we look at the latitudes and the longitudes. Remember, latitude is your lines that run across. Many of us tend to forget that, eh? And longitudes is your lines that run down. Oh, maybe I'm not doing it in geographical terms. Latitudes from west to east, longitudes from north to south. And what we're aiming to do is to find the grid reference of a position. If I had to put something down here, okay, we want to find out what is the grid reference there in order to find out and use it. And you must know we're going on to the GIS era, etc. And it's easy to just locate using all those things. All right. And the intersection gives us a position. All right. The intersection gives us a position. That is a grid reference. So here, remember, these are the big lines of latitudes and longitudes. In between, there's more lines of latitudes and longitudes. So we're trying to find out along this, there's my point here, and along that, what is a grid reference at that specific point where the two lines intersect? Okay, some brief things again, which you know. Lines of latitude measure the distance north and south, okay? And lines of latitude tell us the degrees and how far north and south of the equator we take place. Remember, the equator is here, it's 0 degrees. As we move this way, it increases 30 degrees, 60 degrees, and of course it increases in that way, 30 degrees, 60 degrees. You getting the picture? All right. And then lines of longitude obviously are this way. And we've got the Greenwich meridian, which is 0 degrees, and of course it increases as we move out. All right. Let's look at an example here. Coordinates grid reference. Very important to note that when we do grid reference, we look at the conversions. And one thing we've learned is that 1 degree is equal to 60 minutes and 1 minute is equal to 60 seconds. All right? So if I had to look at this, always at the corner of our maps, right? I always use the left-hand corner. On the side, you will see that refers to lines of latitude. I'm going to write LAT. And this refers to the line of longitude. All right? And remember, these figures, we'll always get southern hemisphere maps, okay? Or maps of a part of South Africa, so you'll always deal with south and east. Okay? This gave us a brief description of how we can just break them up like 10, 20, 30, 40, 50, and we can assume our seconds. All right? So if we look at this, in this one, already latitude is 26 degrees. And then we look at the minute. On the side, you also got those little blocks where it gives you the minutes. In this case, we're looking at this feature. And here we notice it's between 45 and 46. It's not totally 46 at the moment. So it's 45. And there it's cutting across here. If you divide your block into 10, 20, 30, 40, 50, 60, you'll notice that it's near the 10, just above it, so we can assume it's 12 seconds. On the longitude line, we look at 29 degrees, and the feature is found between 0 and 1 minute. So it's 0 minutes, it's not 1 at the moment. And if we break it up into little blocks of 10, 20, 30, 40, 50, we can see it's slightly above 40. Therefore, we got the answer of 41 seconds. Now, I'm going to show you another little one here. With regards to this one, how did we get, or why do we measure? If you want to work on a more sort of accurate measurement and accurate coordinate or grid reference, in this one, we can look at it down here. Now, first of all, I looked at what do I have on this. This is an abstract of the map. I have, for latitudes, I have 25 degrees. It's between 35 and 36, so I have 35 minutes. Remember, those are your minute signs or areas. And then I want to know how many seconds or minutes or point of a minute it is south. Then I'm looking at the other way, and that is 27 degrees. That's showing you my longitude lines. It's between 12 and 13. 13 minutes, and I don't know how many point of a minute or point of a second it is. All right? South. Now I need to find for this and this. So how do I work that out? Number one, I must remember that for my latitude, it's 35 and somehow degrees sort of latitude, all right? And for the longitude, it's 2712 and a certain amount for my longitude. So what do? I measure for the distance starting from the 35, okay? And I measure to my point. I'm actually looking at that point that I want to find a grid reference for. I took this and I measured and I got 12 millimeters. So if I had to put 12 millimeters, and what is the size of my block? Because I want to find out the ratio. The size of my block for latitudes is always 37 millimeters. So I put 12 over 37 millimeters, and all I do is take my calculator and I say 12, of course I need to switch my calculator on first, divided by 37, and I got an answer of 0.32, which is equal to 0.3. All right? Once I've worked that out, I go on to my longitudes. I know my longitude is 27 minutes. I do apologize, 27 degrees, 12 minutes. And then I measure from my 12-minute line to the point that I want to find the coordinates for. In this case, I found it's 14 millimeters. I always have to measure the distance between, or the size of my block for longitudes, in the sense that because the Earth narrows on the top, it can change. Let's say I've measured this and I've got 33 millimeters. All I do is I take my 14 divided by 33, and it gives me an answer of 0.42. Okay, so I've got here 14 divided by 37. I'm going to do that again. 14 divided by 37. All right, gives me an answer of, I'm sorry, I'm making a huge blunder here. We said it's 33. Remember, the lines between the two is 33. So I'm going to redo my calculation. I think age is catching up with me. And I got 0.42. Okay? All I do down here is I take these two as it is down here. All right, I'm going to find a spot and maybe write over the diagram. Okay, I've got 25 degrees, 35 point. And you see this little point here? I just take this 3 and I add it there, and it's 35.3 minutes south. And then all I do is I take my next one, which is 27 degrees, 12 point. And I've got 4.2, which is 12.4 minutes east. And that's how I express my answer in degrees and minutes. And I showed you earlier on how you can estimate and put your answers in degrees, minutes, and seconds. Okay, guys, this sort of comes out in multiple choice. Okay, if it's multiple choice now with the new system, it's going to be 1 mark. Of course, if it comes in interpretation, it can be 2 marks itself. The next thing we're going to look at is magnetic bearing. Okay, there's actually 3 steps to magnetic bearing. With regards to magnetic bearing, it's actually equal to true bearing plus magnetic declination. All right? So it's actually the measurement of the angle between the magnetic north line and the line joining the two places. I will show you step by step because this may not sometimes make so much sense to you, but when I demonstrate, you can see what I'm doing here. So my first step is to find the true bearing before I look at magnetic declination or anything of that sort. Let me start with that. Let's take a question here. Locate spot height 1248 in B4 and spot height 1328 in B7 and determine the magnetic bearing of spot height 1328 from spot height 1248. Remember, another important thing here, and it'll come out for 7 to 8 marks, a lot of marks. It can be at least 10% of your paper because your paper is out of 75. If this question, so we have to be very careful. The word from tells you that you are standing at 1248 and you are looking at spot height 1328. So the from point is where you are and you're looking at that, and that's how you're going to get your bearing. Okay, let's look at it. So when I looked at the question, let me just get the question again. All right, determine the magnetic bearing of spot height 1328 from spot height 1248. Okay, of course it moved slightly. Remember this, and of course it takes some technology also, and sometimes it slips, but this little arrow or this little cross should have been at that point. Okay, so what I'm looking at here is that if I'm standing at 1248 and I'm looking at 1328, and of course I do apologize, this line should have come in down there. I must make sure I draw it properly. Okay, so when I'm looking there, first step is on the dot of spot height 1248. If it's a trig beacon, you draw it through the center of the trig beacon. I draw my cross right through. Make sure my lines are straight and perpendicular, right through the from point, which is 1248. After I draw my cross, I draw a straight line as I've done here to join to spot height 1328. Once I've done that, then I am now ready to measure true bearing. Okay? True bearing is actually the measurement from the true north, which is a fixed position, in a clockwise direction, right up to the line. Okay, remember we said at the beginning, it's a measurement from the true north in a clockwise direction right up to the line joining the places. And magnetic north would be adding the magnetic declination. So I measure this angle. All right, I do take my protractor and I measure this angle. If you got one like this, you have to then assume if your lines are straight, that's 180, and then you measure this angle and you add your both. Preferable, get a full circular protractor, okay, so that you measure the whole angle. Please note the zero line, if you're measuring, must be on the true north. You understand? And then when you're measuring this way, after you've done that, the zero line must be on that line, so you work the two out. In this case, you got right through and you add the two, which adds up to 302 degrees. I'm sure all of you know how to use a protractor. So I've already worked out that my true bearing is 302 degrees. But remember, the formula stated magnetic bearing is equal to true bearing plus magnetic declination. Now, on the side of your maps, you will have this little information. It's always there, and in every exam, you will get this information, all right, on your topographic map. It tells you about the contour interval, and just below that, it gives you the mean magnetic declination. This one was 15 degrees, 57 minutes west of true north, and it was taken in 1997. Learners, do not worry about the month. Whether it's December, or whether it's July, or whether it's August, or whether it's January. Don't now change it to 1998 if it's December. It will still be 1997. For our exam and testing purposes, we're not doing point of a year. We just take it as a full year, and even in matric, you'll get tested like that. All right. Then we got another piece of important information. And maybe I better use my eraser here. I always make a mess of the papers. All right, let me take this off. All right, let me get back to my pen. So 2 pieces of information. The first thing is that it's west of true north, 15 degrees, 57 minutes for the month of 1997. And the second important information is that the annual change is 2 minutes westwards. Now, learners, don't try and learn this off. A simple technique to tell you whether you need to add or subtract. This is the magnetic declination. Learn it off this way, the MD. Okay? And the easiest way to remember this, the true north line is a fixed line, and the magnetic north is a line that moves. So if this line moves westwards, what happens to the angle? It gets bigger. So westwards we add. If this line moves eastwards, the angle gets smaller. So eastwards we subtract. I know many learners try to just learn it off, and then comes an exam, do we subtract eastwards or westwards? Use the information on the map, and it will make more sense to you, and you'll never forget it. So we've got all this information. But when we're finding out magnetic bearing, we have to find out for the current year. Obviously, the current year, and it doesn't have to be stated in the question, learners. You must know that you do it for the current year. Current year is 2013. The map was produced in 1997. So very clearly, you find out, number 1, difference in years, which is 2013 minus 1997, which gives us 16 years. So from the map to now, when the map was produced to now, it's 16 years. We already know the mean annual change is 2 minutes. So the total change of the magnetic declination from 1997 to now, how do you work it out? It's 2 minutes every year, westwards. 16 years have passed. So very simply, it's 16 times 2, which gives us a change of 32 minutes. Now I've got my total change, right? Now I can find out the magnetic declination for 2013 and not 2011, all right? What I do, I take my original one, which is 15 degrees, 57 minutes. That was taken in 1997. And I add 32 minutes to it, all right? 32 minutes, because my change is westwards. And what do we do westwards? When it changes westwards, the angle gets bigger and we add. Okay, so 50 degrees, 57 minutes plus 32 minutes, and I hope my calculation is right there, and yes it is. Okay, I added those two, and it gives me 15 degrees, 89 minutes. Learners, we cannot leave it like that. We have to convert it. Otherwise, we lose marks. So, very quickly, if I add this 2, it works out to 89. Remember, learners, some of you are so used to the calculator. All you do is you try to convert and you say, I know there are 60 minutes in a degree. So 89, quickly press, 89 divided by 60. And it gives me 1.48. In this case, learners, you cannot use the calculator, but it's going to give you a decimal. And we want it in degrees and minutes. So you have to do it manually. Some practice for you, for all of us, in fact. We've got too used to this. How many times does 60 go into 89? It goes there once. So we have 1 degree moving over. And what's left? 29 minutes. That's my remainder. So it's 16 degrees, 29 minutes. And learners are happy. They feel they've got their marks. Learners, beware. We have to write west of true north. If we do not write that, then our answer will be incorrect. Remember, we're dealing with South African maps. It'll be west of true north. Other places it could change. So learners, please note you must write that in full. Now we're ready for magnetic bearing, because magnetic bearing is magnetic declination plus true bearing. Here you don't have to reflect west of true north, because you're finding magnetic bearing now. Originally, you know, it was 302 degrees for true bearing, and the magnetic declination was 16 degrees, 29 minutes. You add them both, all right, and you got an answer of 318 degrees, 29 minutes. Learners, I could go like this. 1. I could go 2. I could go 3. I could go 4, showing the plus sign. I could go 5. I could go 6. I could go 7. A lot of marks. Remember, you got the true bearing wrong, you're going to lose marks. Please, you must show every step, but it does involve a lot of marks, learners. All right? Let's look at the next one, scale. Okay, you've done this from primary school. You understand? And you know already. So I'm going to go briefly through this in terms of the different scales. All right, you've got the fraction scale and the ratio scale. All right, fraction stroke ratio. We hardly get these shown on our maps, the fraction scale, but sometimes you use fraction scale for intervisibility, which we will talk about later. All right, intervisibility. It'll pop up later. Most occasions on our maps, we get the ratio scale. Just giving you an example down here, guys. On the topographic map, you see 1:50,000, and you will get 1:50,000 maps. When in exams for map work, you will always get a 1:50,000 maps. And orthophoto is generally 1:10,000. Quick thing here. Let's see if you can work it out at home. Which scale is bigger? I know you all said it's the 1:10,000. Please don't get confused, eh? This means the reality is brought 50,000 times smaller, and this one is brought 10,000 times smaller. So obviously this is the bigger scale. Okay, let's look at the next scale, and I'm going to put a little heading here, the line scale. All right, you find them at the bottom of the map, okay? It's actually a straight little line, all right? And it's divided into little sections. Okay, and of course it's very accurate. For instance, this could be 10 kilometers, 20 kilometers, and of course that'll be 40 kilometers. So when I measure my distance on the map, and maybe I got, and let's say the distance between each one is 1 centimeter, and I've got 2 centimeters. All I do is I take my ruler, I put my 2 centimeters. Oh, that's actually 20 kilometers. So I just take my little measurement in centimeters, I put it here, and I get my actual distance. That's the line scale. But I do note that we use the the ratio scale the most. Word scale, last one, is expressing it in the words. Okay? Please, learners, we had this question once in a final exam in grade 12, and we had such a massive failure rate. We said express the the scale of the map as a word scale. And learners said 1 centimeter on the map represents, or 1 centimeter on the map is equal to 50,000 centimeters. And that is wrong. We need to give it fully. It's 1 centimeter on the map, all right, is equal to 50,000 centimeters in reality. Okay? A little conversion here which you need to remember. Okay? We can express the scale in different ways. 1 centimeter is to 50,000 centimeters, or 1 centimeter is to 500 meters, or 1 centimeter is to 0.5 kilometers. Okay? All this is the same, because 50,000 centimeters is equal to 500 meters is equal to 0.5 kilometers. Okay? Then the orthophoto map, if you look at that, it's the same thing. 1 is to 10,000 centimeters, 1 is to 100 meters, 1 is equal to 0.1 kilometer. All these units are equal, and we need to use them to make our methods shorter. You understand? Whenever we find that it's necessary to use the scale using the kilometer or the meter, we must be able to use it and know it. Okay? Let's look at this. I use the map of Dundee here. Okay? But generally, any map you could use would create the normal scale, and the top part there was Dundee. Okay? This was taken from a Dundee map. The scale of the topographic map is 1 centimeter is to 50,000 centimeters. And if you looked at that, the orthophoto 1 centimeter is to 10,000 centimeters. So state the scale of the topographic map, and this can come out in your multiple choice questions. Learners, so just beware. Okay? 1 is to 50,000 centimeters. And the next one, state the scale of the orthophoto map. 1 is to 10,000. These things come out. Generally, they come out more in multiple choice questions. We give you a few options and you have to choose. And generally, it's for, so just pull this down. Okay. Generally, it's for 1 mark. Okay, that would be 1 mark. Which scale is bigger? There's that question that we spoke about earlier on. Obviously, it's the orthophoto map, because it's bigger because it's reduced only 10,000 times. All right? Whereas the topographic map is reduced by 50,000 times. Okay? Another one that can come out as a multiple choice question or as an application question. If the application question is 2 marks, the next one would be state the scale of the orthophoto map, not necessarily the topographic map. And learners beware. All right? Because as soon as we hear the word scale, we think 1 is to 50,000. Remember, you can get your calculations and you can get tested on the scale of orthophoto map. So it's not 1 is to 50,000, but when you look at your answer, it's 1 is to 10,000. As a word scale would be 1 centimeter on the map. And I'm going to get to my pen again. 1 centimeter on the map represents 10,000 centimeters on the actual ground or in reality. People, I know this is a simple thing, the scale, but the scale is involved in so many calculations. All right? And if we don't know the scale, because of that, we could get so many things wrong in the map work. Okay? A scale of a topographic map is 5 times larger than the orthophoto, is 5 times smaller than the orthophoto, is 10 times larger than the orthophoto, or is 10 times smaller than the orthophoto. We know the orthophoto scale is larger. So the scale of topographic map is 5 times smaller than the orthophoto. Some simple exam type questions. For this is a multiple choice, definitely 1 mark. Okay? Let us go on. Calculating distance. Okay? Here we're going to focus on straight line distance, and therefore this little piece which always gives us little hassles, we can put away one side. Okay? So, the steps here would be, we'll measure as some people call it about the crow flies. We always say the crow flies in a straight line. Unless the crow is drunk, I don't know, maybe it wobbles a bit. But generally we learned that the crow flies in a straight line. So, we take our ruler, if we're given 2 points, we take our ruler and we measure the distance between the 2 points. And of course, then we apply it to the scale. Okay? Now let me show you that. All right, as we said, as the crow flies, we use a ruler to measure the distance between the 2 points in centimeters. We convert the centimeters reading to kilometers by multiplying by 0.5. If it was an answer that we needed to convert, where we had to convert to meters, then we multiply it by 500 meters. So it will change all the time. Okay? The formula, I'm not going to go through that yet. I'll show you as we do the formula. Map distance times scale is the actual distance. Or in short, you don't have to write it in full, MD times S. Okay? Let's look at an answer here. This one was actually calculate the straight line distance between 1268 and 1282. Of course, I've exaggerated these things so it look clearer on your television screens. The actual measurement when we measured the boat was 3.8 centimeters. All right? So obviously I know I've got my my map distance. Now I need to multiply it by the scale. Okay? Right. Very quickly, and if I want to measure it in kilometers, I know many teachers will state to you, and they're 100% correct, that centimeters can't multiply by kilometers and things like that. You have to show it in millimeters. Okay? But you can just do a straight multiplication, and we do accept it in the final exam. This is the correct procedure. It's 3.8 centimeters multiplied by 50,000. Okay? In the sense that it's correct 2 units of the same units has to be multiplied, which gives you 190,000 centimeters. Okay? And then, of course, when you're converting it to kilometers, you have to move 1. And let me get my pen there, correct? You have to move 1, 2, 3, 4, 5. And therefore, you've got your 1.9 kilometers. Okay? And of course, when you want to convert to meters, then of course, you know, you move 1, 2. Because there's 100 centimeters in a meter. All right? And that's how you move it, and that's how you convert it. Okay, this is the correct way to do it. We do accept the other way where it's straight. 3.8 centimeters times 0.5 kilometers, and you got your answer of 1.9 kilometers, or 3.8 centimeters times 500 meters to get your answer in the sea. The answer is correct, but this is definitely the proper way of doing it. I'm giving you a little of the shortcut there. Okay? Calculating area, same process. Okay? You use the ruler to measure the length and multiply by the scale. And you use the ruler to measure the breadth and multiply by the scale. Okay? And of course, if your answer requires you to have it in kilometers, you convert to kilometers. If your answer requires it in meters, you convert to meters. Just be careful what the examiner is asking for. Okay? Now, obviously after that you multiply the length and the breadth. So you'd get your answer in kilometer or kilometer squared or meter squared, depending on the unit. All right? Let's look at an example. So the formula then is length times scale times breadth times scale. Many of the learners ask me, but sir, what if you wrote length times breadth? I generally tell them, it's right, it's length times breadth, that's area. You understand? A is equal to that. But I tell them, and I'm sure if they're listening out there, that I mark it wrong. Okay? Not that it's wrong. Because what generally happens, if we write length times breadth, learners forget to multiply it by the scale. So learners, although that is right, I would prefer you writing this formula so that you do not forget that I need to multiply it by the scale first. Okay? Another thing is, which is the length, which is the breadth. The longer one is always the length and the shorter one is the breadth. All right? Don't forget that. So that's how it's easy. No matter which way it sits, longer one length, shorter one breadth. Let's take this one. I've just used this piece of the area covered by the orthophoto. All right? And then I measured from there to there. Okay? And I've got 9.8 centimeters. I measured from there to there and I've got 7.4 centimeters. This would obviously be my length and that would be my breadth. Okay? Of course, the next step is to implement the formula. Okay? Let us look at it here. My formula, area is equal to length times scale times breadth times scale. Okay? Obviously, if you want to do it the proper way, which is the best, you understand, 9 times 8 centimeters multiplied by 50,000 centimeters because you're multiplying in the same units. Okay, that's my length. And of course, my breadth is 7.4 centimeters multiplied by 50,000 centimeters. Okay, there's it here. Eventually, my length came to 490,000 centimeters and my breadth 370,000 centimeters. Of course, if I convert it, remember I move 5 spaces to convert from centimeters to kilometers. 1, 2, 3, 4, 5. Okay? Because there's 100,000 centimeters in 1 kilometer. So I have to move 5 zeros. Okay? I've got 4.9. And if I move 5 here, 1, 2, 3, 4, 5, I've got 3.7 kilometers. When I multiply them, they gave me 18.13 kilometers, and that is my area. Now, learners, I don't know why on many occasions we forget the square. One thing you must remember, you've done all these steps and you don't just put kilometers and not kilometers squared, you actually get it wrong because it's not the right answer. Now, what would I look at here? I could go this way. 1, 2, 3, and I could go 4. Okay, that would be my conversion. I could go 4, I could go 5. Okay, I can get up to 5 marks for this. Okay, which is a lot of marks. So the marks range between 4 and 5. And quite a bit of marks you can obtain from this by simply just following everything properly. Let's look at the next one. Map index, also known as map code. Okay, it's found at the top of the map. All right, I'm going to give you an example of the one from Rustenburg, West. Okay, now what does this mean? The 25 is the latitude. If you look at the top left-hand corner of your map, you will find 25 written there. Okay, 27 is the longitude. And these figures exist on the map. Do you understand? This tells you about the big block C and the small block A. Okay, obviously you got the same thing on the orthophoto, just that you got a photograph number. Just remembering that the orthophoto is part of the topographic map. So many orthophotographs make one topographic map. So this is photograph number 20. Okay, so let's look at this index. All right, let's look at this index. Now, you saw here 25, 27. This is how it sits on the map. 25, 27. Okay, and it's big block C, big block C down here, and small block A, small block A down here, because we have this big block or this big square or rectangle that's divided into A, B, C, and D. That makes my big block D. And of course, each one is divided further, which gives you my small blocks. And that's how we got 25, 27 CA. 25 latitude, 27 longitude, like a normal map on the corner. Okay, 25, 27, of course. And then we move on to big block C, all right, and then small block A. Okay. Okay, let's look at the sample questions on map index or map code. All right, the first question here indicates state the map index of Rustenburg West. Learners, this is straightforward. If you're using the map of Rustenburg West or any map for that matter, you will find the map code written at the top of the map. Okay, in this case, when I turn back to the map, okay, can you see 25, 27? Let me just erase it a bit here. 25, 27 is written there. So it's basically, you take this information and you give it. All right? Next question. Determine the map index of the town that can be found to the southeast of Rustenburg West. All right? If we look at this, we already worked out Rustenburg West, which is 25, 27, big block C, small block A. Now we're looking at the town, and I'll go back to the question, southeast. Okay, let's look at it here. This is southeast. So we're looking at this little block here. Okay, so first of all, I need to look at, does it fall within the same block? Yes. Has the latitude changed? No, it's still within there. So it's 25. Has the longitude changed? It's between 27 and 28. It hasn't changed. So it's 27. Now, has the big block changed? It's still in the big block. So it's C. Has the small block changed? Yes. It's no more in A. It's not in B. It's not in C. It's in D. And there we have it. We have our little map code. If it comes out in multiple choice, it's 1 mark. Let's look at the next question. Determine the map index of the town that can be found to the northwest of Rustenburg. Now watch, learners, just be careful. It says northwest. So what am I looking at? I'm looking at here. Okay? Now I draw in another block. Okay? First of all, has my latitude changed? No, it's still within the latitude. It's still between 25 and 26. So it's 25. Has my longitude changed? Now notice, this is the 27 to 28. It's gone out of that block. And remember what we did. We always said west, we'll subtract in terms of the longitudes. And when we go east, it increases, so we're going to add on a degree. So here it's 27 to 28, here it'll be 27 to 26. So my longitude has changed, and my longitude now is in the 26 block. Okay. Next thing, if I look at my big blocks, A, B, C, and D. Which big block is it in? In B. All right. Then I divide my block into 4. This is A, B, C, D. And my answer is 25, 26, BD. Noting that my longitude has changed. Okay, that's map index. Okay, learners, and now we'll take a short break. Go get your glass of water as quick as possible, drink it down, and be ready for the next part of our exciting program. Well, I hope you had a nice glass of water and you're refreshed, because the section we're going to deal with now makes you cross. I know many of you out there have problems with this section, and that is your cross sections. And it doesn't have to be very difficult. Today what I'm going to do is I'm going to look at a simplified version of a cross section, because it's easier for me to show you on television in that way. And then you take more complex ones at home and practice with them. Okay, so let me draw a simple cross section for you down here. Right, I want to then quickly draw a few simple lines and then use it. So I'm using my paper so it doesn't go out of my paper, so I can actually use them properly. I'm going to draw simple contour lines here. Okay. And I'm going to put in some contour readings. I'll put this as 1,260, 1,240, 1,220, 1,200. Okay, and very quickly I'm going to put in a line to show where I want my cross section. All right, and I'm going to put it from A to B. Okay, now the first step, all right, is to note that I take my piece of paper and I put it down on my diagram, and I mark off A and B. And then I look at where my contour lines marked off in each one. So I know A is, if I look at my reading, is 1,260. And if I look at B, it's also 1,260. So I've got 2 points of 1,260. Okay? That is my B, that's my A. All right, I then see where my line, my cross-section line cuts the contour again. It cuts it down here, which is 1,240, and this is 1,220, and then here it cuts twice, remember here, 1,200 and 1,200, and then it cuts again here, 1,220, 1,240. I've got all my readings on this. Most occasions when we're doing cross-section, the graph is actually, or the X and Y axis is actually given to you, all right? But another piece of information must be given to you, all right? And that is your vertical scale. Okay, and let's say in this case the vertical scale, or in most cases, the vertical scale is 1 centimeter is to 20 meters, which then means that for every 1 centimeter vertically, it actually is 20 meters. Now, when I looked at my, if I want to draw the whole axis itself, I look at what is my highest reading on my graph or on my contours. It's 1,260, and what is my lowest? 1,200. 1,200. So I know that I don't have to start from 0. I can just start below 1,200 and just go above 1,260. So, of course, I'm using my ruler, and it's 1 centimeter is to. I quickly draw my lines, and I measure my centimeters. That's 1. Of course, I'm just going to exaggerate here. 2, 3, 4, 5, 6, 7. I put in a few more. That's all my centimeters. Okay, down here. And then I draw in my x-axis. Okay. And of course, I know already that the lowest is 1,200, so I maybe can make it 1,180, 1,200, 1,220, 1,240, 1,260, and I'll stop at 1,280, because that's where it actually is the largest. So I have all my markings down here. So quickly I mark it. I'm starting with A down here, which was 1,260. I'm sorry I'm moving it around. You don't do that. Okay? My next point is there, next point is there, next point is there, 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 there. Okay, I've got all my readings. So that's 1,000, next point was 1,240, 1,220, and this one was 1,200, and this is also 1,200, and this is 1,220, this is 1,240, and this is 1,260. I've got all my points. All right, and sometimes it makes it easier, guys. If you're not sure how to mix your points, you can just draw a little grid. Run a grid along here. Maybe I'll use it lightly. Okay, run a grid around here. Fortunately, the pen here cannot do it lightly. So I run a grid, just a normal grid, and I'll show you just running across, across, across. I wonder if I could just do it quickly. Maybe it'll still be dark, but your lines must be light, eh? And I run a line here. And I run a line here. And I run a line here. And here. Okay? And I run a line here. Okay, in the same way as I've got my points, I run my lines across, and across, and across, and across, and I go on. So it made me easier for me to put my points down. All right. Okay, so now I start off with 1,260 must match 1,260, and that's my point A. 1,240 must match 1,240. 1,220 will match 1,220. 1,200 and 1,200 will match. Okay, I put my little dots. And here 1,200 and 1,200 will match. Here 1,220 and 1,220. 1,240 and 1,240. 1,260 and 1,260. So I've got all my points, and I know that is B. Okay? Now, very quickly when I join my points, I have, this is my cross section, I have a valley shape. Okay? And if I look at my point here, the height is decreasing towards the center. So I could have visualized this earlier on. You understand? And I'm going to get my valley shape. But this, in a nutshell, is what is a cross-section. Learners, please note, let's say this cross-section came out for 1, 2, 3, 4, 5, 6, 7, 8. I came out for 4 marks. And I got this section incorrect. I still will get 2 marks out of 4. Let's say it's half a mark each on each point. So I do get part marks for the cross-section itself. So, of course, you'll get more intricate cross-sections at home. Practice, use the same methodology. If they said put a river in, and let's say the river was here, just mark it and write river. But do more complex ones with your topographic maps using the same method. I just want to look at a few here. Look at this one. You can see the height is increasing as we go towards the center. All right? This doesn't follow our contour intervals, by the way. Ours is 20, this is 50. But you can see it, so you can already visualize, guys, that it's going to go something like that, isn't it? And it's going to be sort of stops, isn't it? It's increasing, but it doesn't go right across, because it's increasing in height as we go towards the center. Let's look at this. Can you see it? Guys, there's it here. It increases in height, and there we are here. It's increasing in height. So we visualize our cross-section beforehand to make sure that we're on the right track, okay? Right. Let's look at another one. Look at this one. This also shows an increase towards the center. You notice? Same thing. It's going up. All right? Next one. This is quite a complex one, eh? It goes 400, 500, 600, 500, 400, 300, 300, 400, 5. So it's increasing, then it's decreasing, it's increasing, then it's decreasing. So we're going to get something like this, and then go down and up. Just let me get my pen here clear. Something like that. You understand? You can look at the contour lines and work it out. Let's look at what we got. Can you see it, learners? There's it going up, coming down, going up, coming down. And visualizing it at first. There's my piece of paper to measure it. So cross sections, if you practice with it, and just double check. You understand? Even with a colleague or your teacher, you can master it. And you realize it's marks for nothing in the end when you learn it. All right? Let's look at vertical exaggeration. Okay? That's linked to a cross section. All right? Beside understanding what feature it's, whether it's a hill or a valley, we can test you on that in the exams. We also do other sort of calculations that are linked to your cross section itself. Now remember, if I had to draw a cross section, and let me get my pen going again, all right, and I didn't exaggerate it vertically, if I do the same cross section I did now, it may be something like that. You understand? But what I did was, I created a vertical scale and exaggerated it vertically. So now how does it look? It ended up looking like that. You understand? So exaggerating something gives us a clearer picture about the landscape itself. All right, there we have it here. It says, gives us a bigger than the horizontal scale. Cross-section always drawn with without vertical exaggeration. Hills and mountains will be very flat, and it will be difficult to see the landscape in detail. Okay, that is your important thing, to exaggerate. Everything in map work has a purpose. Let's look at the formula for vertical exaggeration. Vertical exaggeration, which is also known as VE, is vertical scale over horizontal scale. Now, if you're using the topographic map, the horizontal scale will always be 1:50,000. Okay, if you're using that. If you're using the orthophoto, it'll be 1:10,000. Please note again, check which photo or map you are using and use the scale accordingly. Vertical scales can change. In our last one, the vertical scale was 1 centimeter is to 20 meters. Okay, that's how we exaggerated it vertically. Okay, let's look at this. Let's look at this cross section. All right. And we know I'm not going to, first of all, the horizontal scale will vary between the orthophoto and the topographic map, depending which one you're using. All right, the vertical scale can change also. In this case, in our cross section, it was 1 centimeter is to 20 meters. If you guys remember, I just want to go quickly to that. All right. If you remember this one, we said 1 centimeter is to 20 meters, so we'll use the same one. All right. Okay. Now, let's do a calculation. All right. We know that the vertical scale is 1 centimeter is to 20 meters. We know the horizontal scale, because we are using the topographic map, is 1 centimeter is to 50,000 centimeters. Okay? Now, we have one problem. We have this in centimeter, we have this in centimeter, and we have that in centimeter. Let me just put another 0, all in centimeters. But we have this in meters, and this can't work, learners. So we have to convert this one to make it all in centimeters. Maybe straight line distance, etc., you can use different units. Yeah, it just doesn't work with scales. So my first step is I need to convert. 1 centimeter is to 20 meters is equal to 1 centimeter is to 2,000 meters. Knowing that or 2,000 centimeters rather, I do apologize for that, that is centimeters, okay? Knowing that there are 100 meters, or rather 100 centimeters in 1 meter, okay? So 20 meters will be equal to 20 centimeters, okay? Now I'm set. I apply my formula. But when I'm applying my formula, I don't put it as a ratio scale. I put it as a fraction scale, because in ratio scale, mathematically it won't work. There's my vertical scale, as expressed as a fraction scale, 1 over 2,000. There's my horizontal scale, expressed as a fraction scale, following the formula, 1 over 50,000. We know that it doesn't work if we do it that way. We have to invert and multiply. You know that already. Okay, so it's 1 over 2,000 times 50,000 over 1. Our zeros cancel off. 1, 2, 3. That leaves you with 50 divided by 2, which is 25, and times. So the exaggeration was 25 times, making the picture clearer. So the bigger the exaggeration, the better or clearer the landscape. Okay? So this exaggeration was 25 times. Don't forget to write the word times. Intervisibility, a very simple one. The word is longer than the steps that you need to take. Intervisibility refers to whether one can see a given place from another. Okay? You can also use the cross section here. Let's go back to some cross sections. All right? Okay? I'm going to look at this one. All right? And I'm going to create a little exercise here. I'm going to say, determine the intervisibility of A from B. So I'm standing at B and I'm looking at A. And I want to determine the intervisibility. All right? I can write a little question here and extend my page a bit. All right. Say, determine intervisibility of A from B. So I look at it. I'm standing at B and looking at A. Is A visible from B? Yes, it is. I can see it on my cross section. So my answer, all we'll read is that A is visible from B. That's my answer, learners. But I can't say B is visible from A. That would make it wrong, because the question stated, determine the visibility of A from B. So you say A is visible from B. Let me create another point here and call it C. And now I say determine the intervisibility of C from B. Then my answer will be a different answer. C is not visible from B. As simple as that. C is not visible from B, because there's a hill in there. So All you need to look at whether you can see one point from the other point. But please note, you always use the from point. And you say the other point is not visible, like A is visible from B, or C is not visible from B. And that's basically your intervisibility. Straightforward and simple. Okay. Gradient, we can also use it on a cross section also. Or you can use it on any 2 points. Remember, this is the average gradient. You can never get an exact gradient because land keeps on undulating up and down all the time. So, how do you work out average gradient? The formula for average gradient is vertical interval, which is actually the difference in height between 2 points. And horizontal equivalent is the actual distance. All right, so vertical distance and horizontal distance. For short is VI over HE or VD over HD. All right, let's look at an example. I've got these 2 points, all right, on my little sketch or abstract of a map. And I want to determine the gradient between these 2 points. So remember my formula, okay? It's VI over HE. My first step to find out VI is to find out the difference between the two. Remember, it must be a positive. You take the bigger distance and minus the smaller distance. So in this case, it's spot height 156 minus spot height 152. With spot height, the number is actually the height. So there I have it here. Can you see it? And I got 204 meters as my final answer. So that's the difference in height. For HE, it is the actual distance between the 2 points. When I measured 5.5 centimeters, that is the map distance. So my formula is straight away the same as working out straight line distance or actual distance in a straight line form. Now, please note, I took this 5.5 centimeters and I multiplied it by 500 meters. Remember I told you about scales earlier on? 1 centimeter is to 50,000, 1 centimeter is to 500 meters, 1 centimeter is to 0.5 kilometers is the same scale. But why have I used 500 here? You may ask, learners. Why I'm doing that? Because the top answer for VI is already in meters. It'll be appropriate for me to use the meters instead of converting. And we notice with this, I know mathematically it doesn't make sense. But with learners getting so many zeros, they always mess up this question. So we do allow it like this. Okay, so to find the actual distance is 5.5 centimeters, which I got down here, multiplied by 500 meters, which gives me an answer of 2,750 meters. So I need to look at it now, learners. Do I have my VI? Yes. Do I have my HE? Yes. Can I now work out? Yes. I say 204, that's my VI, divided by 2750, that's my HE. Now you may notice that there is something on the side here. Why do I do that? Just remember, learners, gradient we have to express as a ratio. The vertical distance in comparison to the horizontal distance. 1:something. So always we have to bring one figure down to 1 to express it as a ratio. We always bring the smaller figure. In this case, the top one is a smaller figure. All right. And how do we bring it to 1? We divide it by itself. Obviously, what we do to the top, we do to the bottom. So we divided the top by 204. We divide the bottom by 204. So it's 204 divided by 204 is 1. 2750 divided by 204 is 13.5. This is the answer we got from there. And eventually we express it as a ratio, that 1:13.5. That means for every 13.5 units, horizontally we change by 1 unit vertically. Okay? Now, it's quite a steep gradient, this. You must remember, if we take it in kilometers, for every 13.5 kilometers, we change by 1 vertically, which is quite steep. So this, when we ask you to, and we can ask you to interpret it, we say, what does this mean? It means that for every 13.5 units that you travel horizontally, there will be an elevation of 1 unit. It's quite steep. But the bigger this figure, the more gentler the slope. Like if I go 1:250, you understand? It's a gentle slope. Okay, the smaller the second figure, or the horizontal equivalent figure, you understand? Or the horizontal figure rather, the steeper the gradient. Okay, and we say again, it's the average gradient, because if I maybe take the slope, it won't look like that. It most probably would look like, in reality, maybe it'll be like that. You understand? And then it comes down. So it's an average gradient. We're doing this, guys. We're doing this. We're trying to just forget about the undulating territory. Okay, so that gives us the work for gradient. All right, guys, I'm just going to go back to one thing on landforms. I'd like to show you a few things. We've done quite a few of the calculations, and I just want to show you some few aspects of landforms. Okay, right. Now, in your exam, you'll also be tested on landforms, and there's a relationship between your grade 11 structural landforms, etc., together with this section. And please, that is why you'll find the teachers will be teaching you map work in conjunction with theory, so that you can see it, and you must also study it like that. You must also try to find your relationship between map work and theory. And there's a few issues that we're going to look at here regarding your map work and what you learned in theory and how we identify it. We look at this one here, guys. Very clearly, with contour lines, you can determine whether a slope is gentle or steep. Let's look at this one. Contour lines far apart, can you see it? Hey? Slope is gentle. Contour lines close together, slope is steep. Straightforward. You can even draw a rough cross-section of that, in case you be asked in the future to draw cross-sections. Let's look at the next one. Uniform slope. Now let's look at this uniform slope. These lines are sort of equal distance apart. Can you notice that? The equal distance apart. And if you look at the slope, look at how uniform it is. Can you see it? Because the contour lines are equal distance apart. If you look at this one, you have lines far apart, down here, close together here. Far apart there, close together here. Far apart there, close together there. Which creates a terraced, and sometimes you can look at undulating slope. There's it. Steep, gentle. Steep, gentle. Steep, gentle. A terraced slope. Okay? Let's look at another one. Concave and convex slope. All right? Let's look at this one. How does it start? It starts gentle, contour lines are far apart, and then goes steep. Let's look at it here. Starts gentle and then goes steep. All right? Let's look at the next one here. Starts steep and then gets gentle. All right? Starts steep and then gets gentle. Here, starts gentle, concave, starts steep and then get gentle, convex. Right, learners? I haven't neglected you, but I'm looking more at the board now to show you more of the features here. Let's look at this, butte. Remember when we spoke of the butte and your teachers told you about structural landforms, etc.? The butte, the width, all right, is smaller than the height, okay? So if we look at the center ring of the butte, all right, the center contour line will be very small in comparison to the size of the landform, making it a butte. And there's a nice one from the topographic map, learners. where you can see the center one is quite small. And look at the size of the feature. Width is smaller than the height. I'll show you the MESA just now. All right? Look at the MESA. Now look at this. Look at the center contour line here, how big it is. All right? In comparison to the rest. Can you see it? Meaning the width is greater than the height. Okay? Suppose that is why when you get smaller and smaller, we call you a butte. Okay? Right, can you see it there, guys? And there's one here. Can you see the center? Contour lines is broader, making it a MESA. All right, looking at another one. You know Gap or Poort? It's an opening between a mountain range or a ridges, etc. It's the river that cuts through. It's shown like this. Can you see it? It's cut right through. There's a lovely picture of it. All right, that's a little diagram. And you can see it here. Can you see a river? How it's cut through? And guys, do you notice these things exist? They're on your topographic maps. Use your topographic maps to identify, because you will be tested in exams, in theory and in map work. So get all these sources, like 3 different sources showing it to you here. So it makes it easier to understand. Look at this one, the waterfall. All right, there's your contour lines almost converging, meaning it's a steep slope along this river. This is a river here. A very steep slope. So it's going like this, and suddenly at that point it dips, and the river is flowing. What's going to happen? The water is going to fall. And obviously when water falls, it's a waterfall. All right? So it's steep down there, and that's where you pick up on those features. All right. A few questions here, guys. Before, I know we're running short of time, but I want to do these few questions before I say my bye. Identify the feature marked E on the topographic map. All right. If we look at this one, E, we can see the center ring is not very big, okay, compared to the whole size of it. Therefore, it is a butte. You understand? It's on your map. It's one of the past maps. I think that's a map of Rustenburg West. All right? Is this inclined or horizontal strata? Now, that's straight theory question, isn't it? From the theory you learn. But we can test you in map work. You know structural landscape. You know mesas and buttes are on horizontal landscape and not inclined. So it's a butte and it's horizontal strata. All right. In cases when it's application, you can get 2 marks for these things. Okay? Identify and describe P and Q. When you looked at P, all right, and looking at Q, all right, you can see that with P, or rather with Q, the lines are further apart compared to, with P, the lines are further apart. Here, the lines are closer together, and it's coming down one slope or one hill. All right, so it seems more like a ridge. If I had to look at this, it looks something like, I put my hand like that, and of course it's steeper here. Can you see it? Steep there, gentle there, which tells us it's a more or less a homoclinal ridge or a cuesta. And this is your dip slope, and this is your scarp slope. All this you learned in theory, and this creates a ridge which is homoclinal or known as your cuesta. Look at this one, we're still using contours here. Locate the Rustenburg hiking trail in blocks J7 and J8. I'm looking at, there's a play area down here. Okay, and then we're looking at, you are a novice hiker who is very unfit, and you are given a choice of doing a hiking trail C or D, starting at F. In which hiking trail would you choose, and give one reason for your answer? If you look at these 2 hiking trails, there's one from C to F and from D to F. Obviously, you'd look at your contour lines to notice which one is steeper. Okay, and in this case, when you look at it here, You look at D. Why D? It's more gentle, contour lines are far apart. So it's more gentle, all right, compared to this one, which is far more steeper, all right? Okay, learners, let's look at question 7.4.2. Identify the landform from where, at F, where the hike will start. And if we look up here, we can see a river going through, all right? So clearly, that is a river valley. Okay, you can see the contour line, steep, and then going in and going in, all right? And we can even identify your features from there. And you know what, learners? We can even maybe make you draw a rough cross-section of this area from there to there, all right? A rough cross-section. And if you draw a rough cross-section, it'll be something like that. And we can ask you to identify the feature from a rough cross-section. So you don't have to draw cross-sections all the time accurately. It could be a rough cross-section. Learners, you would have realized today that there's a lot of different types of map work techniques, but they're not out of this world. There's few simple things that you need to do, and I'm sure your teachers are doing it in class. Each time they're teaching you a theory section, they're relating the map work to it. You understand? So you're seeing theory and map work working hand in hand. Secondly, in map work, it's practice, learners. You can't sit and learn your stuff out and then go and write a map work exam. You're not going to perform well. You need to take maps and practice with them. That is why your teachers in class, each time they finish a section in theory that's related to map work, they give you a set of maps to use. So you're seeing it. So practicing makes perfect. And map work is there to score high marks, especially the calculations, because you know what calculations are going to come out, and it's not a lot of them. Learners, I hope it has been very beneficial for you, and I hope those marks are going to go up. All the best.